In this video, we will derive the isentropic efficiency relationship for turbines using the first law of thermodynamics. So, when we're talking about the efficiency of turbines, we're going to look at two turbines. We'll have the actual adiabatic turbine and the ideal isentropic turbine. So remember when we talked about isentropic efficiencies, we say that they have the same state 1. So you see here our state 1 is the same for actual and our ideal. But then we're trying to figure out state 2 of our actual to compare it to our ideal. For our ideal, what we know is that it is isentropic. So that means that the entropy at state 1 is going to be the same as the entropy at state 2. And we know that because when we compare for the isentropic relationships, we know that the pressure at state 2 will be the same as the pressure at 2s. So those are two definite properties in our ideal isentropic turbine. Based on those two, we can figure out what the other properties are, and then we can use these properties to determine the efficiency of the turbine. So to get the turbine efficiency, we start with the first law of thermodynamics, and we'll use the 1 in the 1 exit. You can get this equation from your reference data card. It's our basic first law for an open system, 1 in the 1 exit. First assumption we're going to make is that it's adiabatic, because that's what we said. We're doing at adiabatic steady flow devices. We're also going to say that there's the kinetic energy is going to be negligible. The change in kinetic energy is negligible, and the change in our potential energy is going to be negligible. Okay. So then this equation reduces down to the power is equal to the mass flow rate times the change in enthalpy from 1 to 2. Notice how we've flipped the 1, not going from 2 to 1, it's going from 1 to 2. That's because it was a negative on the left side, and we got rid of that negative, so we flipped the signs around here. If we compare our actual to our ideal, that'll give us our efficiency. So our efficiency is the actual work to the ideal work. So ideally, we would put out a certain amount of work. We would get all of that energy transfer. In actuality, we're going to have some irreversibilities, so our work is going to be less. And if our efficiencies are always going to be from 0 to 100%, so the numerator has to be smaller than the denominator. So we supplant those equations there from above, our reduced equation, and we see that the mass flow rates are going to be the same, so we get rid of them, and that's our simplified equation for the efficiency of a turbine. This is equation 7.4 in your text, and it's also located on your reference data card.